ratio from each AP. You might imagine that in a practical network where we have lots of pairs or lots of transmissions, then the chances that this condition is going to be satisfied is very low. So if that's the case, then what we thought of is basically we can just focus on a subset of transmissions at each time that satisfies this condition. And that's basically the basis of our information theory link scheduling, or ITLIQ scheme that, again, we came up with based on that condition. So this is in general like a greedy algorithm that basically decides sequentially on whether to schedule each access point or not for transmission. So let's say at each time slot or at each scheduling interval, we first order the pairs according to some priority list. So for example, here you see that access point 1, user 1 has the highest priority on the top, and then access point K has the lowest priority. So because of this notional priority, we just activate the first AP. We don't ask any questions of like what is its channel conditions and so on. But going down the list, we look at each access point UE pair, and then we basically check the interference that that UE is getting from the higher order APs and the signal to noise ratio of its own link to its own AP. And then we check whether its interference to noise ratio satisfies this condition, basically being less than or equal to the square root of its own SNR. So basically this means that it's not receiving a lot of interference from higher order APs. And at the reverse side, we also need to check that the access point is also not causing much interference at higher order users. And the criterion here is similar to this one, but the difference here is that we are looking at the outgoing interference from this AP to higher order users. So if you look at these two conditions, if you put them together, let's say if you just multiply them by each other, you will get exactly the same condition that we had here, right? So it's kind of, I mean, what I'm showing here is like a sufficient condition for making sure that treating interference as noise is kind of good enough in this network. So let's say we check access point 2, we decide it's not safe to schedule that. We go to the next one, we decide to schedule that, and then we complete the list going to the whole number of list of access points, basically. So the question is, in general, in a wireless network, we don't have similar number of UEs to APs. We have like lots of more users than access points, of course. So in order to handle that, we kind of use the notion of proportional fairness or PF based users scheduling. So first we do the associations as regular based on maximum SINR or maximum RSRP. So basically, roughly speaking, it means that each user gets associated with its closest access point, and we assume that these associations are fixed during the communication period. And then what we do at each scheduling interval dynamically over time is we calculate these PF ratios, which is going to be the estimated instantaneous rate of each UE over its long-term average rate. And I'm sure you're familiar with that. This gives you kind of a notion of how in need each user is to be scheduled. So for each access point, we look at its user pool, and let's say this user in the user pool of this access point has the highest PF ratio, and then we just say, okay, let's just focus on this UE and then forget about the rest in this scheduling interval. This is just assuming, by the way, that we have a single frequency resource. So if you have multiple of them, we can just do this in parallel for different subbands, let's say. And then once we have this, then we end up with a...
How do you even compute the instantaneous rate? Is it just based on like you're taking into account the interference? You're assuming it's just omnidirectional transmission, and so you just have a fixed interference level from the APs. You're assuming they're always on.
Yes, so that's a good question. So we are assuming omnidirectional, yes. So everything is ISO, let's say, and also in terms of how we estimate it, we are, as I mentioned in the first slide, we are relying on the feedback from the UEs, and we assume that like every, let's say, 10 or 20 steps, they measure some long-term average interference. I'm going to talk about it more in the next section, but the UEs basically report some feedback reports in terms of the SINRs, for example, that they measure over time. And
so in other words, like the UE, like a UE schedule doesn't really care whether the neighboring AP schedules UE1 or UE5. From its point of view, the interference is the same.
Exactly.
So it would be unaffected by that schedule.
Exactly, yes. And it's going to be kind of an average notion of interference that's happened so far. So we're assuming that it's a consistent operation of APs. So we kind of have a pattern of what the interference is going to look like for each of the UEs, just roughly speaking. Yeah. So once we have that, we have one user per access point, and then we can just apply our ITLIQ algorithm. And then what we carefully do here is that we use these PF ratios as our ordering criterion. So basically, if this user across the entire network has the highest PF ratio, this access point gets the highest priority in our ITLIQ algorithm. And then we do this over time. And the PF ratios, of course, will change, and then the user selections will also dynamically change over time. So to kind of show how it performs, just a quick set of results. We consider a set of access points denoted by n, and then we assume that on average we have 5 users per access point, but it's not going to be uniformly like separated between, I mean, the user pools are not going to be partitioned exactly uniformly across the APs. That's fine. Some other parameters I'm not going to go through, but the metrics that we're looking at are like twofold. So first we look at sum rate, basically the summation of the throughputs of the users across the network. And the second one is the 5th percentile rate. So basically if you plot the CDF of the user rates, we're looking at what is the rate that 95% of the users get at least that. So that's kind of a notion of fairness for us to not basically kill the users that are at the cell edge and have like very bad channel conditions. And we just use a simple benchmark for now to compare with. Basically, we use a full reuse scheme, which basically just does the PF scheduling of the users. But in terms of the power control, let's say just there is no interference management involved. So all access points are active with full power. And what we observed here in this setting is ITLIQ with this notion of proportional fairness ordering of the access point is helping in terms of fairness. So here, for example, here you see that on the x-axis we have the number of access points, and on the y-axis we have the percentage of sum rate gain over full reuse. So in terms of that, we don't see much gain, but if we look at the 5th percentile rate, basically how fair we are across the users in the network, we are seeing that we are getting gains of like 20% or more, especially with higher densities of users across the network and the access points. So, so you see that the sum rate is hurting because we are trying to be fair across all the users in the network. So here, for example, in this extreme on the right-hand side, we have 150 users in the network in a very limited area that we are trying to be fair. And that's why we take this hit in sum rates, but we are like boosting in terms of the 5th percentile rate or being fair across them. Okay, so, like after joining Intel, basically after doing my PhD, we're thinking of how we can improve over like what I showed you just now. And so first of all, it's like the better scheduling criteria. So the decision boundary that ITLIQ was using was mainly linear. So if we look at this comparison of the interference to noise ratio and the SNR in general, so this was kind of the constraint that we were using. And so for example, we were using eta equal to 0.5 and m equal to 1, but you can imagine that we can tune these parameters to get the best performance. And that's exactly what we did also in our work. But if you took the log of both sides to go to the dB domain, then you can see that this is just a linear line, right? So if you have a scatter plot of INRs versus SNRs, if we're below this line, let's say we just schedule that transmission. If not, we do not schedule that for now. But you might think of well, like what about general nonlinear decision boundaries, or if we have, if we can come up or if we can learn basically better scheduling criteria in terms of how to schedule, not just based on a linear decision boundary like that. And second, or perhaps more importantly, we want to make this decision-making distributed. So what I mentioned to you was basically we have a central entity that has access to all the information across the network, and that is going to decide on the, let's say, the scheduling actions of all the access points across the network. And That might be kind of unrealistic because we're doing this every millisecond and that needs to be so fast. And so here the question is really how we can basically distribute this decision making across the access points so that each access point gets some local view of the environment and then makes its decision, for example, in terms of power control or in terms of user selection on its own without caring about like what other access points are going to do, similar to what ITLIQ was doing. So for that, we kind of, this brings me to the next section. We thought of how we can use multi-agent deep reinforcement learning to address this problem. And just to briefly go over the problem statement again, we have again a set of access points and a set of users. Let's assume that the user pools are separated or partitioned already between the different access points across the network. And then, as I mentioned, we want to have a distributed scheduler at each access point, which again, the goals are similar. We want to, again, maximize the throughput. We want to be fair across all the UEs, even though we are making decision-making distributed among the APs. And we assume that the users pools are going to send us, again, feedback on the network state. I'll mention what the feedback reports are. But each distributed scheduler is going to get a subset of those feedback reports. And it's going to make these decisions, again, link scheduling, power control, user scheduling, similar to what we had in the centralized case as well. And as you can see, we have like multiple objectives and multiple decisions that we need to make, again, dynamically at each millisecond. And therefore, really approaches based on machine learning can be useful here. And that's exactly why we first thought of using reinforcement learning to address this problem. So in this part, I'm going to specifically focus on joint power control and user scheduling. So at each interval or at each millisecond, each access point is going to decide on what transmit power to use. That's going to be a power control problem in downlink. And also it might decide to turn off. So in that case, we don't need to do any user selection. But in case it decides to be active, then we need to basically decide for that AP which user it's going to serve in that interval. And for that, we, as I mentioned, relied on multi-agent deep reinforcement learning. As you can see, we kind of equip each of these APs with an agent, let's say, which is going to be distributed. And it's basically a neural network that, like all the reinforcement learning agents, is going to interact with the environment, which is going to be our wireless network here. In terms of, it's going to get some observations from the environment, which is a function of the entire global state of the environment, which you don't have access to at each step. But the observations are going to be, for example, the measured UE SINRs, the UEPF ratios, and so on. And in terms of the actions, basically it's going to be what is the selected UE for each of the agents and what is the transmit power and so on. And then in order to kind of tell it whether its actions were good or not, of course, we need to rely on a reward mechanism for the agents. And here we use kind of a global reward for all of the agents. And we use a weighted sum throughput. I'll exactly mention what we use. So it's not that each agent is going to get an individual reward for itself. So it's kind of a class of multi-agent reinforcement learning algorithms where we just have a global reward. And we want to kind of allocate that reward to different agents as we train the network. And again, similar to all reinforcement learning systems, basically we have this interaction loop of getting the observations, taking the actions and getting the rewards, and the agents is going to be trained over time to kind of take the best actions in order to maximize the system performance, or in this scenario, basically optimize the reward that it gets from the environment. Okay, so let's talk about the observations that each...
Can I ask you a question? A quick question. So for this slide, do you consider the other agents as part of the environment? Or do you also consider the interaction between different agents while using deep reinforcement learning?
That's a very good question. So we do consider the interaction between them because our training is centralized. So we kind of gather the experiences of all the agents, and the way that we train is basically using an experience buffer which has access to all of them. And also we use parameter sharing. So it's a single neural network that's deployed on all of the agents. So because of that, we really take care of the interaction between them. Yeah, thanks. Okay. So we assume that first each of the agents or each of the APs, I just use them interchangeably because each AP has an agent for itself. So each agent is going to receive at each, like over time, basically some local observations from its associated users that you see here. And we specifically rely on just 2 feedback reports from each UE to its serving AP. And so going back to Jeff's question on like how we measure the SINR, so we assume that we define the SINR of each user at each time step like this. So it's a standard definition for the channel gain in the numerator at step T between API and user J. And Pmax is going to be the maximum transmit power. And then in the denominator, we have this long-term interference, long-term average interference of UEJ at time step T. So it's basically an exponential moving average of the interference that the UE has basically received so far during, let's say, an episode. So beforehand, we do not have information about the interference exactly that's going to be experienced by each UE at each time step. We just rely on this notion of long-term average interference to kind of have a sense of, statistically speaking, what's going on for each of the UEs in the network. And the second observation that we assume that each UE basically sends to its AP is its weights that we define as the inverse of its long-term average rate. And the long-term average rate is going to be defined similarly to the long-term average interference here. And basically, again, we have the exponential moving average of the achieved throughput of each UE, basically, again, so far up to time step T. And so these constants alpha I and alpha R are basically some positive constants that are close to 0, like 0.99, for example, depending on what is the like time variation that we want to have, or the smoothness of variations, I would say, that we want to have for each of these terms. Okay, so now, so as Aaron pointed out, we want to kind of also consider the interaction between the agents. And for that, what we kind of consider some level of communication between the neighboring agents. Because we are in a wireless network, we might have access to a backhaul interface. And what we assume here is that basically each agent is going to exchange its observations over time with a set of agents that are physically closest to itself. And we use this notion because, again, because we're talking about wireless interference, if 2 agents are close to each other, we're assuming that the impact of the decisions that they have is really going to be high between themselves. So we have this parameter n, which is kind of independent of the actual network size. And once we drop the access points in the network area, we just create this observation exchange graph, which says that, for example, each agent is going to get observations from a set of small n agents that are close to it. For example, here you see that we have 6 agents, and we set n equal to 3. So agent 1 is going to receive observations from agents 2, 3, and 4, and so on. You see, for example, that agent 3 is like at the central location, so it's kind of having more interaction in terms of exchanging the observations with its neighboring agents. So just to emphasize, this graph is going to be fixed across the entire episode of communication, so we're not going to change it dynamically over time. Okay, so so I mentioned the local observations that each access point is getting from its own UEs, and then because of this observation exchange, we also assume that each access point is also going to get some observations from its neighboring APs based on the observation exchange graph that I showed you in the previous slide. But you might ask the questions of how kind of we ensure scalability, right? So because we might have load imbalance, for example, one access point might have more users, the other one might have fewer number of users. So we want to make sure that our agent is applicable to different sorts of scenarios. And for that, we kind of, what we do is we first, again, use the proportional fairness notion. We first, at each time step, the access point is going to sort its UEs in its user pool according to their PF ratios. where the PF ratio is again defined by the weight times the log of 1 plus SINR. This is the estimated instantaneous rate of that user. And just to recap, these are the two pieces of information that the user feeds back to its own AP, right? So the AP has really access to these, this information, and it can estimate what the PF ratio of the user is going to be. So it sorts the users according to that. Again, the PF ratio, the higher the PF ratio, the more in demand the user is to be served in that time step. And then what we assume is that each AP is going to just focus on a subset of users at each time step, where that subset is basically the top K users in terms of the PF ratio, right? And again, this is small K is a parameter that's going to be independent of how many users each access point has and how many users we have in the entire network. So here, for example, K is equal to 3 in this example. So putting them together, basically, this is going to be the final observation vector, observation structure that's input to each agent at each time step. We have a set of local observations from the top K users of the access point itself. And we have the information and the observations from a set of N remote agents. And each of them will give us a similar kind of observation structure. So if you just count them together, we have an observation space dimension of 2n plus 1 times K. So K is the number of UEs per AP, N is the number of remote agents per AP. And you can see that this doesn't really depend on what the actual network size is. And this really helps us if we have like a multi-layer perceptron or just a regular neural network as our agent, then we can really use a fixed dimensional observation, regardless of how many nodes we have in the network. Okay. So I mentioned the observations that are fed back to the agents. And so typically what you see in reinforcement learning research is that the agents basically have access to observations at each time step. But of course, we're talking about a wireless network, so we need to kind of take care of some of the practicalities here. So we're assuming that the observations are going to be undersampled. So the UE is basically going to track its weight and SINR. It's going to measure them every time step, but in terms of how it reports it to its AP, it's going to be kind of undersampled. So you see that we have a feedback period here based on which the UE is going to basically sample its weight and SINR, and then it's going to report its feedback reports to its AP. But there is also going to be a delay in terms of when the feedback is going to arrive at that access point. So we also take care of the feedback delay, and we'll incorporate that in our framework. And moreover, we have, I mentioned the observation exchange among the agents. So we also assume that there is a backhaul delay. Of course, the throughput of that interface is going to be high, but there is going to be delay there. So we also assume there's a backhaul delay here that basically each AP is going to send its users' observations to other APs with a certain amount of delay as well. Okay, so in terms of the action space, so we consider discrete action space here where we kind of quantize the non-negative transmit power interval. So again, just to recap, we have this maximum power constraint of P max. This open interval of 0 to P max, we quantize it potentially non-uniformly if you want into small P power levels. And then given that we have PK plus 1 number of actions potentially, where again, K is the number of UEs that we focus on for each agent at each time step. So this is basically what these actions mean. So the first action is just, this is just a +1 here. So it's just going to be off. So if the agent is going to be not going to be active, then there is no user selection involved. But then we have like all these PK actions are basically the combinations of different power levels and different users that the agent can select. So basically we have the agent going to be active at power level number 1 and serving user with the highest PF ratio. And you can see that the difference of P power levels and K users. So we have PK actions if the agent is going to be active. So again, you can see P and K do not depend on the actual network size. So again, the action space size also does not depend on the size of the network or how many users, how many access points we have in the network. So observation space, action space, both of them at the input and output of our agents are fixed dimensional, and that really helps us to kind of make this approach is scalable in terms of how many agents we have and how many users we have. Okay, so I guess the last thing here is in terms of the reward that we give to the agents. So here we really rely on a centralized reward, which is the weighted sum throughput for all the agents. And the way we define it is basically going to be the throughput each user gets weighted by the inverse of its long-term average rate raised to some power of lambda, which is a hyperparameter for us between 0 and 1. And this really helps us kind of strike the right trade-off between the sum rate and the cell edge performance, right? So if we just, I don't have the values here, but let's say we just set this lambda equal to 0, so you will get the reward of sum rate. And that's just going to encourage the cell center performance. But if you just set it equal to 1, then you will get a PF-based reward, right? So it's going to be the product of the weight and the rates, and that is going to encourage cell center performance, cell edge performance, sorry. And here what we use is an intermediate value of 0.8 that we found giving us the best performance here in terms of the trade-off that we're seeking here. And there is an edge case here because we're doing the decision-making in a distributed way. It might be the case that in some time steps, all of the agents decide to turn off. And of course, that's a waste of resource. We don't want that to happen. In that case, we penalize the agents with a negative reward, which is, I think, if I remember correctly, is going to be the negative of the PF ratio of the highest PF ratio user of that TP, of all of the TPs. And so that way we kind of make sure that when we deploy the agents, they will not turn off all at the same time. But again, remember that they're doing this decision-making in parallel, so they do not know what the other agents are going to decide. Okay.
I'm sorry, on this last slide, is this a typo or am I not understanding something? That when you have lambda rho here equals 0, you said then it's just a sum rate reward, right? Which should encourage cell center.
Oh, yes, sorry, it's a typo. Yes, yes, yes.
Okay.
Yes.
Okay.
Exactly. Yep, good. So, so yeah, so 0.8 is basically kind of more towards the cell edge performance, and that's like what is exactly we are going after, but we also want to take care of the average performance across the network.
Okay.
Okay, so in terms of how we train this, as I mentioned, we want to train our agents to kind of make sure that they work well across a wide range of scenarios. And so for that, we do this centralized procedure for training, where we have this centralized experience buffer that I mentioned, which collects the experiences of all the agents across the network. And then we are going to, as I mentioned, again, have a single neural network and a single set of weights and biases, or the parameters for the neural network that we are going to give all the agents basically across the network. And like in other, like most of the reinforcement learning research, we are considering an episodic sort of training, where we, which each environment instantiation or each episode is going to be a random drop of access points and users in the network. And that's going to be run, again, different from episode to episode. So we drop them. We then go through the episode. Basically, we have, let's say, hundreds or thousands of time steps where the agents are going to make their decisions based on the observations they get and then get some rewards. And then we just inject those experiences into our experience buffer. And then once in a while, we basically do this neural network updates based on a mini batch of samples from the experience buffer. And then we push the updated weights to the agents. And because of this randomness, there are like lots of different scenarios of, let's say, cell edge and cell center, or combinations of those that the agents are exposed to. And this really gives us like the ability to train the agents so that they kind of perform well across a range of different scenarios. Once training is complete, we have this distributed execution phase. It can be both in simulation or a real environment. Of course, we haven't tested this on a real environment, but we tested it on simulation. So each agent, again, just to recap, is going to receive local observations from its UEs. and some remote observations from its neighbors. And then it feeds it to its agent neural network, and then it's going to take its action independently at every time step. So that's kind of the distributed execution phase. In this phase, you might think of maybe fine-tuning the agents if we are in a real-world environment, but in the simulation, we don't do that. So we just freeze the parameters of the neural networks, and we just test them after training is complete. Just set up parameters for showing you the results. Again, I won't go through all of these, but we look at this range of scenarios from like 4 to 10 APs and 24 to 40 UEs. We kind of look at a fixed geographical area. So as we increase the number of APs or UEs, we're kind of densifying the network accordingly. And each episode is going to be run for 2,000 intervals. So we have 2,000 time steps, each one, let's say a millisecond. So we have like 2 seconds per episode in terms of the real actual transmission time. And we consider the feedback period to be 10 intervals. So really the feedbacks are updated every 10 intervals. And also in terms of the delay for the feedbacks, we assume that the feedback delay between the user to its own access point is 5 milliseconds, and also an additional 5 milliseconds for the delay in terms of the backhaul for exchanging the observations between different agents. In terms of the agent structures or the reinforcement learning agents, we use a value-based, basically a DeepQ network agent, and also a policy-based advantage active critic or A2C agent. And both of them we use for both of them we use a fully connected neural network with 2 hidden layers and 128 nodes per hidden layer. And in terms of basically how many users we focus on at each time step, we just focus on the top 3 UEs for each access point at each time step. And also in terms of the remote observations that each agent gets from its neighboring agents, we assume that it's also equal to 3. Again, regardless of how many agents. So even if we have 10 access points, we just assume that the observation exchange just happens with the 3 closest agents of each access point. And of course, this is going to be applicable to any kind of scenario, but for now, we just focus on binary power control, which means that P is equal to 1. So we either turn off the access point or just activate it with full maximum transient power.
Maybe for the path loss model, are you using a single slope or dual slope?
A dual slope path loss model, I believe.
Like with like 2 and 4 or something like that? Path loss?
4, I think so, yes.
Okay. Appreciate that. Thank you. That's
yeah, that's important. Yeah. Okay. So in terms of like what we compare to, I think at this point you are familiar with this. Full use is going to be PFS scheduling of the users across the access points, but there's no power control. So all of them are active with full power. So on the other extreme, we also wanted to try just as vanilla TDM, which is basically round robin scheduling of the users. It's like kind of, you would imagine the kind of fairest algorithm you can think of in terms of how you allocate the users, the resources across the users, but on average, you would get a very bad performance across the network. So that's kind of gauge how we're doing in terms of the 5th percentile rate or the fairness among the users. And like as a centralized baseline, we also look at ITLIQ that I mentioned. So it's again PFS scheduling of the users, and we use that centralized greedy algorithm to decide which APs to turn on and which of them to turn off. So just to compare these, the full reuse and TDM give you low complexity and they are distributed. So you don't need to coordinate between the access points in terms of the decision making, but we won't get a good performance in terms of the trade-off between the average performance and the worst case scenario. But ITLIQ is good in that sense in terms of the complexity. It's kind of quadratic in terms of how many access points you have, and also implementation wise, again, it's going to be centralized. So that's kind of like the extreme points that we want to compare our algorithm against. So first, I just want to show you the training results with 4 access points and 24 UEs. So on average, we have 6 access points, 6 users per access point, but again, it's not exactly uniformly partitioned across the access points. So here, blue curve on the first on the left-hand side, we have the sum rate or the average sense of performance across the network. On the right-hand side, we have the 5th percentile rate, or kind of the cellar scenario, or the worst case performance. Blue is TDM, so you can see TDM is very bad in terms of the average performance. It's better in terms of the 5th percentile. Red is full reuse, and ITLIQ is in black. And you see again the trade-offs that we see here. ITLIQ is kind of giving us a very good kind of 5th percentile performance, as I also showed you in the beginning of the talk. In terms of the agents that we have, green is showing the DQN agent, and the purple one is showing the A2C agent, and the x-axis, by the way, is basically the training epoch. And each epoch is, I believe, a set of 50 episodes that we have. So you can see that there is going to be a trade-off between, like, even the agents. For example, A2C is getting a better sum rate performance, but DQN is getting a better 5th percentile performance. It's even outperforming ITLIQ. And again, remember that ITLIQ is centralized, but our agents are going to do it in a distributed way, and they really managed to do that in a good way so that they are kind of, again, allocating resources fairly across the users in the entire network without being aware of what the other agents are going to decide. So again, this is what's happening during training, but after training is done, as I mentioned, you can freeze the agent parameters and then can test it on different scenarios. So here's a set of plots for, let's say we have 4 access points, and then we increase the number of users in the network from 16 users to 40 users. So on average, we have 4 users to 10 users per AP. And the color code is the same as previous slide. And by the way, the shaded regions are the standard deviation across 5 individual training runs. And again, you see that in terms of 5th percentile rates, DQN is beating ITLIQ. It's having a little bit of loss in terms of sum rates, but it's really a decent performance, again, imagining that this is all done in a distributed way. So this is the case where we train on a scenario and test on the exact same scenario, but I mentioned that we can, because of the fixed size of the observation action space, we can go beyond that. So we can fix a number of access points, and we can test on a scenario which we haven't seen during training. So this is showing, for example, some curves where we train on, let's say we train a DQN on 4 access points on 16 users only. And then we try to deploy it in scenarios with, let's say, 40 users. So we are able to do that because, again, we are trimming the observation and action space based on the top users in terms of PF ratio. And you can see that, and also vice versa. So we can train it on a denser network with 40 users and then deploy it on a sparser network. So you can see that across the board is kind of scalable. You see that like maybe other than this DQN, which was trained on 4x16 case, the performance is kind of decent. So you really don't need to be careful about like how many users you have in the training scenario. As long as you train it well on that, then if in the deployment phase you suddenly happen to have more users in the network, you are going to be fine. So same goes for the number of APs. So let's say we fix a number of users at 40, and then we increase the number of access points. So here we're really increasing the problem size because we're increasing the number of agents in our multi-agent setting. And you see kind of the same trend that A2C is able to get a better performance in terms of sum rate, and DQN is going to get better performance in terms of the 5th percentile rate. But there is some gap here in the like 8 agent case, which might be attributed to the fact that we are not exchanging observations maybe well enough, because we're just limiting the observation exchange between the agents to 3 agents. And as we increase the number of agents, you can imagine that might hurt us in terms of performance. And similarly to the previous case, we can again train on, let's say, 4 agents and then test on 8 agents, or we can vice versa, train on 8 agents, test on 4 agents, and so on. So again, you see that this approach is going to be scalable no matter how many agents we have in the network during deployment. So an interesting thing that we observed is basically interpreting what the agents are doing in the network. So This is a plot of, this is just a scatter plot of, let's say, different agents in our testing phase. And on the x-axis, we have, let's say, we focus on each agent, and we look at its top UE, and we have the SINR in dB of that UE on the x-axis. And on the y-axis, we have the weight of that UE, which is the inverse of its long-term average rate. So the color coding is basically showing what action the agent took. So green is basically when the agent was on, basically serving any of these sub 3 UEs, and red is basically off. So it decided not to transmit at all. And you see that there is kind of a clear boundary here. That is kind of, the boundary is going to be weight times SINR equal to a constant factor. And, but if you really think about that, weight times SINR in dB is going to be roughly the PF ratio. So the agent has really learned a linear decision boundary on the PF ratio without being explicitly told to do so. So that's kind of an interesting observation that the agent came up with after this training phase. Okay, so if there are no more questions, I guess I can jump into the last part. So this is kind of a more recent work which we did on using learning power control policy.
So Navid, you know, as somebody who followed your ITLIQ work back, you know, 5 years ago and thought it was pretty good, would you say an accurate summary of this work is that you were able to achieve ITLIQ type performance with a decentralized online algorithm?
Yes, that's kind of fair to say. I would say we approached that performance.
I mean, it's comparable. I mean, it's getting kind of, you know, especially for the 5%, right? Which is what you're trying to do with ITLIQ, right? Is trying to protect vulnerable links and avoid strong interference links.
Right. So, and also we attempted to do ITLIQ in a distributed way and failed. So it's really not clear how we can really leverage those conditions to make each AP decide on its own whether to transmit or not. So that's really a hard problem to do. But yes, maybe in summary, yes, we can say that.
This is what I'm kind of one of my I just want to make sure my takeaway was at least not inaccurate. I mean, there's obviously a lot more here, but I just wanted to make sure high level.
That's a fair assessment. Yeah. Okay. So just touching upon this last part, we used graph neural networks to basically learn power control policies in an unsupervised way. So that's kind of different from using reinforcement learning. So here we really don't have access to any kind of reward mechanisms or like label data to kind of tell us what the optimal power control should be. So again, this is just a preliminary work. So we go back to the single user case. We assume that we have small m APUE pairs, and we have the, again, notion of channel gains and the channel matrix H. And the SINR of each user I is going to be like this. So just want to highlight that the transmit power of access point I we denoted by PI, which is going to be a function of the channel matrix. And this is going to be the Shannon capacity, of course, log of 1 plus SINR. And that's going to depend on what is the channel gains across the network and what is the transmit power levels of each access point, basically. So here what we wanted to do is kind of a parametrized power control formulation. So we have short-term fading in our, I mean, of course, we had it all over the talk also. So here we really need to focus on the ergodic channel, ergodic average rate, sorry, of the users across time because of the channel variations over time. And because of that, we have this formulation for the power control problem. So we have as our objective function a convex utility function of the UE's ergodic average rates, U of X. And basically each X is going to give you the rates that user I is getting on average over time. We also have this minimum capacity constraint, CI min, as we denoted, which is kind of basically a lower bound that we want each user to satisfy across the network. And the power constraint is going to be P max. And then we have this phi function here, which is the power allocation policy, which takes as input the channel matrix. And then it has a set of parameters theta, which we can assume maybe it's a neural network. And then at the output, it's going to give us the power control vector basically for different APs. And here the goal for us is basically to find the set of parameters theta, which leads to the best performance in terms of the utility function. So before showing you how to solve this, I just want to mention that we have this channel matrix, and that really leads to this notion of a graph, an interference graph, as we call it, where each vertex corresponds to an AP-UE pair, and then the edges between them is going to correspond to the channel gains between these different access points and UEs across the network. So we can really use this graph as an underlying graph for a graph neural network architecture, which is based on first a graph shift operator S. And S is basically going to transform our matrix H, for example, to another matrix of the same size and same order. For example, you can just take in the channel matrices, the channel matrix, and then, for example, output the SNR or INR values or something like that. So we kind of have this matrix S, which is going to give us the weights of the edges in our network. And then we have this graph convolution operation, which takes as input a signal Y on different nodes of the graph. And then we have a set of filter coefficients here. Basically, we are kind of aggregating the neighboring nodes feature vectors. And then we are going like from 1 hop to 2 hops or 3 hops or even more. So these filter coefficients are the set of parameters that we are trying to actually learn here in this algorithm. And just to make sure I emphasize that this function g of h needs to preserve the ordering of the nodes and the sparsity pattern. So for example, if you have a weak interference link, then you want your S to kind of reflect that fact as well. So now having defined the graph convolution operation in the previous slide, we can now concatenate these layers, like L of those operations, and also with some pointwise nonlinearities. And then based on that, we will end up with this power control policy. And so basically what we have is as our input an initial feature vector for the nodes, and at the output we will end up with some, let's say, power control levels for the different APs. So we used here as input features for the nodes just some dummy values of just equal to 1, which doesn't have any information, because all the information we really need is already captured in the weights of the edges in the graph. And as I mentioned, the set of parameters that we're trying to optimize is going to be the union of all the filter coefficients that we have in different layers. And the final nonlinearity here that we have at the Elf layer, at the output of the GNN, that can be chosen, for example, using, let's say, a sigmoid function, so that we make sure that we satisfy the power constraints for the access points. So for example, you can just use a sigmoid and then just scale it by P max so that you're sure that it lies in this desired interval. But you might ask the question why we use graph neural networks, and there are kind of two things here, like different than what I showed you in the previous part of the talk, where we have just a regular MLP. The GNN is kind of invariant to the size of the network. So if you add more nodes, for example, more access points, or if you have fewer, then you don't need to do any trimming or anything. So the number of parameters or the filter coefficient, that is going to be fixed regardless of how many nodes you have in the graph. And second, and also very importantly, it's permutation equivariant. So basically, if you permute the nodes of the graph and also the adjacency matrix of the graph, then at the output of the GNN, you're going to also get a permuted version of the power control levels. So this is really helpful in terms of training and in terms of training efficiency and sample complexity, because if you look at maybe two networks that may appear different to you, they may really be very close to permutations of each other. And of course, we have graph isomorphism and so on. So, this really means that if you train on one of those networks, it can easily be transferred the knowledge of the GNN to networks which are similar to that, but maybe they are like permuted versions of that graph. So that kind of really helps us kind of scale in terms of sample complexity, especially if you have maybe larger networks. Okay, so back to the optimization problem. We use a counterfactual optimization framework to optimize this. And so first I want to just point out the minimum capacity constraints here that we have. So the main question here is that we don't know really how to set these kind of minimum capacity constraints, right? So if you set them just too loose, they might be just very easy to satisfy. On the extreme, you might just set them equal to 0, so you would effectively have no minimum capacity constraint. But if you have a very kind of dense network with a high level of interference, if you set this minimum capacity constraint at a high level, then it might be just really infeasible to satisfy. So the proposed solution that we have here is basically introducing these factors SI, which we call like a counterfactual slack variable for each of the capacity constraints. So here, SI is a positive variable, by the way. So it means that if we increase SI, then the minimum capacity constraint for the ith user is going to kind of get more relaxed, right? So it's kind of making it more adaptive. But we don't want to just increase it all the way to CI min, basically making this 0. So we also introduce this additional term in the objective function where we also try to minimize the slack variables at the same time, right? So we want to keep this problem feasible. We want to also minimize the value of the slack variables that still make this problem feasible. And to solve this, we first write a Lagrangian function like this. We have the dual variables lambda and mu based on the constraints that we have. And then our goal is basically to maximize the Lagrangian over our primal variables, which are the slack variables, the neural network parameters, the GNN parameters, and the rates, while minimizing it over the dual variables, which are corresponding to the constraints that we have. And we just use an iterative kind of update mechanism using partial gradients of the Lagrangian. So we first update the primal variables, which correspond to the weights of the GNN, the filter coefficients, and the rates. And the slack variables are also updated like this. So both of them are updated using gradient ascent. And then next we update the dual variables, and they're updated using gradient descent. And we just close this loop, and then we iterate until like all the variables have converged. The simulation setting is similar to before. Again, we consider 1 user per access point, but the number of access points is going to increase from 6 to 14 in limited areas. Again, we're increasing the density, and channel model and bandwidth and the same, the other parameters are kind of the same as what we had previously. The minimum capacity constraint, we set it to 2 bits per second per hertz for all the receivers. But because we have the slack variables, those are going to adapt to the channel conditions that we have in the network. For the GNN, we use 3 hidden layers with 4 features per layer and filter size of 4. So it's kind of, roughly speaking, a very small GNN compared to what's out there in the literature. And again, there is no constraint on how we do the power control. We again use just a binary power control policy. You might just view it as kind of a node classification problem in an unsupervised way if you just look at the graph. So we train on 4,000 random drops, and then we finally freeze the GNN and we test it on 500 test drops. So just to show you a quick set of results. So first here is the evolution of basically how the slack variable is evolving during training. So on the x-axis, we have the training drops, and on the y-axis, we have the value of the slack variable for the minimum capacity constraints. And again, if you increase the slack, that means that you're relaxing the minimum capacity constraint, and that's exactly what's happening. So the blue curve here is for m equal to 6. So it's a kind of a sparser network, and you see that the slack variable is closer to 0. So you really are able to satisfy that minimum capacity constraint of 2 bits per second per hertz. That's really not that difficult, but as you increase the number of APs, you have more interference, and this framework really allows the slack variable to elevate itself so that you're kind of relaxing the capacity constraint based on the actual network condition that you have. And in terms of the final performance, again, looking at the trade-off between them, on the one extreme, we have TDM, which again gives us a good 5th percentile performance, performing very badly in terms of sum rates. On the other extreme, we have this WMSE approach, which is kind of an improvement over, again, full reuse. So it does power control based on a purely sum rate objective function. So you see that it gets a very good sum rate, but in terms of 5th percentile, it's performing very badly. And our approach, which is using the GNN, is kind of sitting in the middle. It's not getting like the best of both worlds, but it's kind of in terms of the trade-off, it's performing kind of decently as compared to the two extremes. Okay, so just to summarize, I talked about the set of centralized and distributed algorithms. For interference mitigation, I started with ITLIQ, which was using the network information theoretic conditions for optimality of treating interference as noise, but that was centralized. I then talked about using multi-agent deep reinforcement learning to kind of distribute decision-making across different agents. And I showed you how scalable that is going to be in terms of how many nodes you have in the network. And as Jeff pointed out, it's going to get a performance similar to the ITLIQ algorithm while it's distributed. And also finally, I touched upon our recent work on how we can use graph neural networks to kind of come up with power control policies in a non-supervised manner, and with the slack variables and the counterfactual optimization framework. And before wrapping up, just want to thank my collaborators over the past few years who have made all these works possible. And with that, I'd like to conclude. I'd be happy to take any questions.